So here we go.
Yeah. Hello everyone, my name is Zhirui Hu, and the first problem is that why we use the quantum computing. I believe that all of them you know the applications, one of the applications well. So I present this slide is to say my background is most focused on the quantum machine learning and the QNN. So I think if there is some errors in my presentation, you can interrupt me and let me know, or we can talk after the presentation. First, I will introduce the quantum learning, the basics, and the property. Here is the steps for quantum learning. First, we will define a learning problem and the loss function, and then we will select a learning model. For quantum machine learning, there is a common model. The first part is encoding, and the second part is computation, and then it is to do measurement. And here are two different ways to do training. The first way is to train the model on the quantum computer. It is to say the forward propagation is on quantum computer. The advantage of this way is that we can get the potential on the qubit scalability. It is to say we can encode the data to the qubit. It is an exponential size. But the disadvantage is that it is difficult to optimize the parameters, and due to the limitation for the current resource, the training time is so long. However, the optimizer is still on the classical computer. And then in the medium area, we usually do the training on a noisy simulator. The advantages of training on a noisy simulator is that we can use the accurate gradient descent method. It is more efficient than train on real quantum device. However, there are some advantages, such as the limitation on qubit scalability, and the noise is difficult to be simulated. And then because it is a intermediate method, I think it is difficult to get some insights in the paper. Someone will challenge us that even if we can do the algorithm on the classical computer, why we need to employ them to the quantum computer? So I think it is just a medium method. It is to accelerate our research, but it is not the final. It is not the final solution. Then I will introduce the noise on quantum device. I will take the superconducting quantum computer as a case study. Here is the main two sources of the quantum noise. One is the control noise. As you can see here, it is an ideal X gate. However, due to some reason, such as the pulse cannot be executed perfectly, there will be error in the control part. Besides it is called a coherent error. Besides the coherent error, there is another error that is because of the environment. Because the quantum environment, it should be because of the charge noise or magnetic flux noise or crosstalk, the quantum state will not always be where we are supposed to be. So there are plenty of works that to do quantum noise modeling. Here is T1 and T2 is to describe the decoherent noise. This T1 and T2 is to characterize the noise source and how they impact a given quantum system. T1 is the thermal relaxing time, and T2 is the dephasing time. The thermal relaxing time is to say that when we get a X gate, it is hardly to net the state from the 0 state to the 1 state. It will include some noise, and the vector will be if we use the Bloch spell to express this, the vector will in the sphere, and the dephasing time is to say that if we net the state in the if we let the state use a Harman gate and let them in a superconducting state, we use a phase gate to net to change the phase. It will not do a perfect phase change. It will always has some inaccurate part in them. This I showed this slide is to say that we can use some parameter to describe the process, and then here is another another noise modeling here is another noise modeling method. It is gate error and readout error. It is a kind of statistic method. It is to say that we can implement a gate to the circuit and measurement it and get the error. It is a statistical method, and these two noise model, we can transform we can transform the T1 or T2 to the gate error statistic error. There are other works to do noise model. I think they are different forms, and one is there are main two kinds of model method. One is to describe the process, and another is to describe the result. After the noise modeling, there there are another property for the noise on quantum device. It is fluctuating noise. From this figure, we record the noise from we record a 1 year noise. From this figure, we can say that the noise is changing every day. And the noise on different qubit or on different age is also different. We train a model on the first day and then test it on the other days. We can see that the accuracy will decrease in some days. This is because the errors on some days is large. It might be the gate error, and it also might be the readout error. Different kinds of errors will affect the accuracy. Besides the temporal, besides the temporal heterogeneous, it is still the spatial heterogeneous. We test a model on 2 different backends. We can see that the accuracy on different backends of different days is still different. In order to address the noise problem, we have the first work. The first work is called quantum neural network compression. The first work is a case study of quantum neural network, but it can be implemented on other variational algorithms. Why should we do compression in quantum neural network? First, from the noise perspective, as the gates, this figure is from the IBM summer school. As gates become more, the control error will be accumulated, and the result will be divergent. And then, as the time grows, the coherent error will be several. And then, even if the noise component in the parameter, such as the noise aware simulation, the noise is extremely random and varying, which will also damage the accuracy. I also did the I also analyzed this from the optimization perspective. This is a loss surface on 2 parameter circuit. As I change the 2 circuit, it is this and this. The loss will change, and I draw the loss as the surface. The first figure is the surface on noise-free environment. We can say that it is a surface. There is no point out of the surface. But when we get the process in the noise environment, we can say that there are some points out of the surface. This is because these points are just the points of the parameter. It's just that they are 0. It means that we can remove the gates, and then the errors on this gate will be removed. So the points is out. The points are out of the surface. I sub the first I sub the first surface, and the third figures is the difference of the first one and the second one. We can say that if we remove the two gates, the error is minimized. And then even if we use the noise-aware training, we can use some gradient descent-based optimizer to find the best point. However, it is difficult for the gradient descent-based algorithm to find the points that is out of the surface. So I think it is important to do something that we can remove the gates, which is called the compression. Let's review the compression part on the classical pruning. We can see the first figure. Here is a kind of random pruning. Maybe we can remove the nodes and the weights. However, it is difficult for this kind of pruning to achieve an acceleration on a hardware. So someone proposed the filter pruning or channel pruning which is remove a block of the weights, and which can net the weight to be small, and then we can get the speed up on the hardware. It is called the structural pruning. In the pruning, there is one thing need to do. It is that we need to generate a mask to describe which part need to be pruned. In the quantum area, we also want to achieve a speed up due to the compression. So we want to remove some gates. What is different in quantum pruning? It is the compiler. Because for a single gate, the gate with different parameters will be compared to different circuit lengths, such as if the parameter is on the 0 or 2 pi or 4 pi, the gate will be removed, and if the parameter is times of the pi over 2, the length will be changed, but not the 0. So we call the parameter on something that if the parameter is on something, we can remove the gate. We call it a quantum pruning. And if the gate will be compiled to some length, but it is shorter than the original length, we will call it a quantization. And then we record the length change in a lookup table, which will be used in the following steps. And here is a problem. How can we decide the compression level? So because the compression level is due to the quantum compiler. Each step can be the steps in the compiler. Each step we can do some works. Let's go through the compiler first. This is a input circuit, and then the logical input circuit will be decomposed to basic gates. For different kinds of backend, there are different kinds of basic gates. And then we need to map the logical circuit to the real quantum device. So we need to do the initial mapping first, and then because of the quantum device, the connection is not the two pair. It is not a fully it is not the fully connected routine. So we need to do some routine project. We need to use some swap gate to net the whole logical circuit to be executed on the real quantum device. Then not all of the gate can be executed on the quantum device. So we also need to decompose the logical gate to the physical gate. A different quantum device has the different kind of basic gate. And then the output is the output circuit is built up from the basic gate. At last, the basic gate will be transformed to pulse, and we can do some pulse scheduling. And last, we will get a pulse. The pulse is executed on the real quantum device directly. My first work is based on the gate level compiler. Maybe we can still do some work on the pulse area. So for the quantum neural network, there are two objectives. The first one is to maximize the accuracy of classification, and the second one is to minimize the circuit length. Because we are in initial part, the quantum neural network has limited number of parameters. So based on the property, we use a heuristic metric to get the sensitivity. The metric is that the accuracy multiplication the t. The accuracy is that we would like to get the maximized accuracy, and the t is to minimize the circuit length. Based on the hierarchical metric, we can get the compression level. It is to say that there are several parts of the compression level, such as pruning and quantization. So we need to decide which level we need to do. We use this metric to select the compression level, and then we use a optimizer called Admm to do the optimization. So based on the previous, there are 3 stages. One is to do preparation. This is to do the compression level lookup table, and then we will do the compression, and we will use the heuristic metric to decide which level we will select. And then at last, we will use the Admm-based optimizer to optimize the parameter so that we can get the best accuracy and the shortest circuit length. At last, we will use the compiler to let the logical circuit gate to the physical circuit gate and deploy it on the real quantum device. Here is the result on the real quantum device. We can see that our compression method can make the accuracy not decrease, and the original circuit, the accuracy of the original circuit, the dilution of the accuracy is so large. And then the compression algorithm can reduce the circuit length by 2 times, while the accuracy is also higher in a noisy environment. And I also did it on different backend. We can see the similar observation. So we can conclude that the circuit compression can make the QML model more robust to the noise. My second work is to do compression-aided framework to battle against the fluctuating noise. As we mentioned before, the noise is fluctuating. This is because of the noise in some days is larger than in the normal days, so the accuracy will decrease in these days. We did the experiment on the noise-aware training on the first day. This is the blue point, and I also did the compression on the first day and the test on the other days. There is also accuracy dilution. Although the accuracy of the compression is a little better than the noise-aware training, but the accuracy is still decreased on the days that the noise is big. We further investigate the reason. We can see the 3 days, the noise on the 3 days is different. The first day is small, and the second day is large, and the third day is medium. I trained the model on the 3 days and tested it on the following days. We can see that the model trained on the first day, the model trained on the small noise, we can get the best, the high accuracy in some days. However, they will decrease when the noise is increased, and then the accuracy will come back in the following days if the noise is small. We can also see the model trained on the high level noise. The model on the high level noise, we train the accuracy is higher than that we train on the low noise days. And then we test it. We tested the high level noise on the following days. We can see that the accuracy is still lower than trained on the low level noise. And the medium noise is similar with the medium. The observation on the medium level noise is similar. So we can say that it is important to train a model on one day and test the model on a day that the noise is similar with the previous days. So there are two observations. Models compressed on different noise levels have different performance on the same days, and then models compressed on one noise level have different performance on different days. So noise-aware compression is important. We review this slide is to generate the weight mask and decide which parameter will be pruned. If in the noise organism, if we don't take the noise into consideration, we always choose the parameter that is near the we always choose the parameter that is near to the pruned target. So if we don't take the noise into consideration, we always select the distance is minimized to be pruned. But if we take the noise into consideration, we will add the noise to the distance, and then if the noise is more large, we will have higher potential to move the gate so that the total noise will be minimized. And then let's see the fluctuating noise. We can see the green circle. It is a gate error, and then the accuracy will decrease because of the large gate error. And the yellow circle is about the readout error. If the readout error is large, the accuracy will also decrease. And the cost of noise-aware training compression every day is very large. So I think it can do some clustering to use one or several points to represent the circle. Besides, the circuit is not so large, so we don't need to use all of the qubits and the edges. So there might be some parameter that is not important enough. So instead of the L1 or L2 long distance, I use a correlation to suggest the weight. If the correlation of the noise with the accuracy is large, we will the weight will be large. If the correlation is small, the weight will be small. I use this to suggest the clustering algorithm. I use the simplest k-means algorithm. So the framework is two stage. It is offline and online. For the offline part, I use historical data to construct a repository by clustering, and then use the noise-aware compression to get a model and save the model in the model repository. In the online part, we will select a model from the model repository to do the inference, and the selection of the model can be decided by the distance of the noise on the today with the noise on the model repository. And then if the noise is far from the noise in the model repository, we can generate a new model and put it into the model repository. So the model repository is increasing. Here is the experiment result. We can say that our framework can build against other baselines. From the last two rows, we can see that the offline and online can battle against the without offline. It is to say that the model repository is important and the cluster algorithm is important. We can just use several points to represent the fluctuating noise. We test the model on the real quantum device for the baseline and noise aware training, and our method, we can say that our method can get the highest accuracy. We also compare the training time for different kinds of method. We can say that the accuracy of compression every day is the highest one. However, the training time of the compression every day is so large. So we our algorithm can reduce the training time several over 100 times. Indeed, if there is low offline part, we need to do 7 times. We need to do 7 times training. But if we have the offline model repository, we only need to train 1 time in the online. I also do a ablation study for the distance metric. We can say that our proposed k-means with the weighted distance L1 norm, the accuracy of clustering and the mean accuracy of sample is both of them is higher than the L2 norm. That's all of my 2 works. So here is our conclusion. There are 2 ways to optimize well-rational quantum circuits in the NISQ area. The first one is to build up a robust well-rational quantum circuits. I think there are plenty of works to do them, such as Henry's NUT or the Goose release, the fidelity aware compilation. I think they are both. All of them are in these ways. They're targeted to build up a robust, well-rational quantum algorithm. Use the ways of training, simulation, or search, or compilation. However, there is only several works to do efficient noise-aware adaptation. I think we can put more efforts on this part to do to think how can we adapt our model or circuit to a different noise. My work is an initial work. Maybe we can use different kind of technology, such as transfer learning, to do this. And here is a big problem in my org, because the model repository is increasing. I think if the time is long enough, I don't think we can save a lot of model in the model repository. So I think the transfer learning is important to do something such as the continuous learning or others. That's all of my presentation. If you have a problem, you can ask me.